All righty. Uh, Good morning, or good afternoon, or good evening, wherever you are right now. So, welcome to this EMWorks webinar series. My name is Ahmed Kabir. I'll be presenting this webinar. We'll go through a PowerPoint presentation, and then we'll give a live demo. Then we'll pass to question and answer at the end of the webinar. Okay, so Uh, we have weekly webinars, by the way. So today is we going to talk about how to use EMWorks tools or solutions to design and simulate an actuator, a solenoid actuator, specifically for an automated manual transmission. Okay. Okay. So our agenda is as follows. I'm going to talk briefly about an overview about transmission technology. If you are not familiar with different transmission technologies, transmission types, uh, and then we're going to talk about modeling design challenges. Then to answer the design challenge, we'll see how EMWorks solution can be used to overcome the design challenges, show you some simulation results, and we'll go straight to a live demo of the software. All right. So what is transmission system? Transmission system is meant to allow the engine to stay disconnected from the wheels. You know, your engine is not connected directly to the wheels. It is through the transmission and the powertrain, okay, uh, that your wheels move. So that's one basic reason we have transmissions. Of course, we have variable speed, and the speed varies greatly when you drive your car, but the engine, as a matter of fact, works at the same capacity. It is the transmission that is responsible for providing the required amount of energy at different speeds. The acceleration and torque increase, so the engine provides higher speed and lower torque for the transmission system, which is not useful in smooth car functioning. The transmission system converted into lower speed, higher torque through the drivetrain. Okay, it enables the running of inner and outer road wheels at different speeds when the vehicle moves on a curved path. So that's basic idea of transmission. So you have the engine right here, and then you have the clutch and flywheel in case you have a manual transmission, and this is your transmission. Yeah. So transmission technology. Of course, everybody knows there's manual and automatic. Okay, so manual transmission has some pros and cons, and same thing is the automatic transmission. So the pros of the manual transmission, it's lower cost, lower price, and less expensive to service, is more efficient in terms of fuel, acceleration. It favored it. You can accelerate very fast. So favored by car racing and performance drivers. Many drivers lack the feeling of being in control. There are cons. Uh, Long learning curve. It takes more time. As all know, when we started to learn how to drive, we want to avoid manual transmission. Uh, Lots of practice needed. Okay, and it takes time. It can take a long time to learn how to coordinate between the clutch, gas, and brakes. Okay, it's difficult in driving and stop go traffic. If you are in heavy traffic, is really annoying, as you know, to drive manual transmission. Okay, automatic transmission, on the other hand, higher resale value. Your car, when you try to sell your used car, it is have higher value for your car, easy to learn. It's like a motorcycle, great in traffic, in downtown traffic, it's much easier to drive automatic and widely available. While the cons that it's more expensive, repair cost is higher, and historically, okay, let's say historically less fuel efficient, even though that is changing these days, nowadays. Okay. All right, let's just talk about the automated manual transmission. So to take advantage of both worlds, uh, car manufacturers and engineers started inventing to take advantage of both of them. It is a combination of the manual and automatic transmission. So it's a simple idea. So the AMT, or the automatic manual transmission, has same principle as the manual transmission, except that instead of the clutch work, you have sensors right here. There are sensors, and where the idea comes of replacing the clutch. So by an automatic way of changing the gears. Okay, um, so you need electromagnetic actuator positions directly on the transmission, handling the gate selection and engaging or disengaging the gears. This electric system replaces the clutch pedal altogether. That's where it comes. The importance of our topic today is how to design that clutching, that actuation, uh, right, uh, connected to the gear itself. Okay, it has many advantages. It has a higher fuel efficiency and less CO2 emission. Lighter gearbox, suitable for electric cars, especially. Okay, better precision, less faulty, more adapted to heavy and duty trucks. So that it comes the our topic today is how to design uh, that uh, actuator or solenoid actuator, so to speak. Okay, so what is so difficult or challenging about uh, this type of actuators? Okay, well, uh, you need a high force density, so at least 500 Newton, okay, to be able to replace the clutching and shifting of the gears. Fast actuation, as you can see here, this figure. Okay, uh, the actuation response should be very fast to the force generation command. High force at low voltage, so at 33 volt, for instance, you need to have almost 500 Newton. You need high efficiency and low loss, and you should have a limited heat. So these are the design challenges posed by designing a solenoid actuator for automatic manual transmission. This is very brief. So what we propose to you is to use our solutions. Well, of course, our solutions, it can be used for any actuators. Okay, but in particular, we customized our presentation today uh, to this particular topic because it's very important nowadays, especially with the uh, high demand on electric cars, where many of them they use automatic manual transmission. So our electromagnetic solution, we have the 2D, okay, and the 3D. So both are integrated in SolidWorks and Autodesk Inventor, so you don't have the headaches of the CAD. We have motion coupling, parametric analysis, flexible CAD. We have multi-physics capabilities. So these are some of the benefit of using our solution, okay? And we're going to show you how to use our solution for this particular application, okay? All right. So this actuator, actually, it's a real one. We took a dimension from a manufacturer, okay? And we use uh, this particular actuator, the dimension, the properties, all of that is from a real life actuator, okay? We can give you the reference if you wish, okay? So one thing, one feature, if it is, in this case, doesn't have any grooves or slot, if it is completely axisymmetric, okay, we have this great feature that you can do 2D simplification, okay, and you will be able to do just a cut. In that case, we use the EMOX 2D, and that, of course, uh, it helps a lot because you can run much faster, do larger problems, so on and so forth. So the 2D simplification, this no other vendor has this. Usually they make you draw your 2D or axisymmetric. We don't do that. You actually take the three-dimensional and you just do 2D simplification. And when you do that, okay, this is the process how to do it, okay? Then you end up with from 3D to 2D, then this is done. Just choose the plane, okay? And then you end up with just a 2D geometry, which you can use to EMOX 2D, okay? These are some solution of EMOX, some results from EMOX 2D. You have the flux contour lines. In this case, we did a parametric study with different air gaps. Number of turn, Solenoid specification number of turn, AWG23, and DC voltage 33 volt for different air gaps and showing the magnetic flux density. Okay, this plot, all of this will be demonstrated live just in a minute, okay, when we do the real live demo. Okay, so these are just a taste of the results that I'm going to present later on, but one of them is that you can do parametric study. If you parameterize the air gap, okay, at different distances, air gap, you can see, okay? So we said you need 500, around 500 Newton. Okay? So by doing a parametric analysis, you automatically know that, hey, look, if your air gap is beyond, let's say 1.5 millimeter, okay, it's not going to work, okay, because you're going to need at least around 500 Newton for actuation to be able to do the shifting and the clutching, okay. So one of the conclusion you can draw from the parametric study of the air gap, that not at an air gap that is going to work. It's going to work only to a certain level. Okay, and of course, the smaller the air gap, the higher is the force. Okay. Another set of results is the thickness of the housing. Okay, so this is the housing. Okay, and this is the thickness of the housing. Okay, so you also can do a parametric study for the thickness of the housing. Okay, and based on this, not at any housing thickness that's going to work. So you're going to have a thicker, of course, thicker housing is of course going to be heavier, more material and all of that, but sometimes they don't have a lot of choices. So unless you are 3 millimeter and more of thickness of the housing, you are not going to achieve the required force for the clutching. Okay. Okay. Another set of results Uh, in this case, uh, the current in the electromagnet, okay, you can also parameterize that, and you say, hey, uh, what is the current I need? Okay, so as you can see, you're going to need at least, 6, 7 amps, okay, per turn in order to achieve the actuating force. So of course, the force is the most important thing in this, right? So the plunger has to move up and down, and the whole actuation is based on the force. So that is the most important design criterion that you have to take into consideration. Okay. One other parameterization you can do is what kind of steel. So in this case, we parameterize the steel, steel 416, 12L14, steel 1010. As you can see, also this is this one here for a given for the distance, okay, and this is for the thickness, okay, of the uh, I think this is different for the air gap. I think this is for different air gaps. Wait a minute. Okay. Yeah, I'm not really actually sure about the x-axis, but anyway, it is showing you the force at different for different steel. You're going to see it later on. Okay. This one is the current versus time at different voltages. So you have 43 volt, 33, and 23 volt. Okay, and this is the current. The winding loss, ohmic loss versus time at different voltages, and force. As of course, if you have a higher loss, you're going to have a smaller force. So force versus time at different DC voltages. And as you can see, it greatly depends on the voltage, the DC voltage for the electromagnet or coil. This is more of the same. This is a fixed voltage, looking at current versus time. This one fixed voltage 33 volt. We're looking at this one a different air gap, as we presented earlier, that you need the smaller the air gap, as you can see the red here, the larger is the force. Just presenting the results as a function of time for this transient solution. The other one was the DC, but this one's transient. Okay. Showing more of the same. So this one is showing you the current at different voltages. Okay, that also depends. This is the time, and the current, it definitely depends on the voltage. And this is, of course, this motion. This is motion settings. Okay. This is the dynamic analysis. Dynamic means doing transient, okay, with the eddy currents. So as you can see, the distance, okay, traveled, okay, by the plunger as a function of time at different voltages, okay, and definitely, when you have higher voltages, definitely you have more displacement. Speed, the higher voltage gives you higher speed, okay. Uh, this one comparing the current with eddy on and off. Eddy current is so important. The eddy current here is in the housing, in the plunger, okay, and in the shaft also. Now, actually, the shaft is stainless steel without any, the eddy current is off, but you can see the effect of the eddy current, okay. This one also, the solid loss at 33 volt. So of course, no eddy is the bluish is zero, and you have eddy loss. Okay, this is the solid loss or eddy loss. Solid loss as a function of time, and so the conclusion is when you have solid loss okay, the eddy loss, okay, as a function of time versus uh, applied the DC voltage, okay? So, as you can see, higher voltage gives you higher force, higher, but at the same time, you have to do a trade-off because it's going to give you more loss. Okay, higher loss is going to affect the end results because you're going to generate heat. So this is something that has to be carefully uh, studied and optimized. Okay, the trade-off between the force, speed, force, and losses, because you know at higher losses you're going to have more heat generated. These are some of the field results. This one is magnetic flux. This is eddy off, eddy on. This is 33 volts. As you can see, the penetration when you have eddy on, okay, you have a higher field. And this is the current density, actually, the eddy current density distribution, okay, in the entire structure, actually, okay. This is all using the MOX2D. Uh, so uh, we can see when the this is speed as a function of time, okay? When the eddy is off, okay, we can achieve higher speed, okay, at keeping the voltage constant, 33 volts. So we have to, when we design, okay, we have to find a way to limit the eddy current, or ideally uh, eliminate the eddy current altogether, but it's not always possible to eliminate the eddy current. Sometimes you have to design around it. So this study shows you the effect of the eddy current. This one is the inductance too. So these are some sample results of the 2D, but sometimes you can't help it but do a 3D analysis, like in this case, when this part, include the enclosure, okay, this box, enclosure box, is actually not axisymmetric for whatever reasons. It could be for mechanical reasons, to be able to fit it, to fit your actuator right on top of the gears, okay. For mechanical reason, you can have some slots. In that case, you can't use axisymmetric or 2D. You must use fully 3D, and are well equipped for that. So in that case, we use EMS, okay, uh, with motion coupling. So this is some screenshots. This one is results from 3D with motion coupling, force as a function of time, okay, and we have the displacement and the velocity as a function of time using 3D. This one is the temperature, and of course, as we said earlier, we can also couple to thermal and structural, and we also did a thermal analysis to see the effect of the losses, how much temperature can generate. Okay. This one, we did also an electrothermal simulation with temperature-dependent conductivity. Okay, and this one showing you the evolution of the coil resistance, because if you have temperature dependent, the coil resistance is going to vary, and of course, the higher the resistance, the higher will be the temperature. Okay, these are some results. This is the force as a function of time, and this is the temperature. Okay, this for a different time step. All of that you're going to see it live in a minute, okay? But just see some taste of the results that I'm going to show you in the live demonstration. Okay, okay, that's it. That's it for the PowerPoint presentation. Let's move straight to the um, software itself. Okay, so again, the EMS. This is EMS. This is 3D. This is the EMWorks 2D or EMS 2D or EMWorks 2D. These are just add-ins to SolidWorks. So just in the add-in, you do this only once. Okay, you click on EMWorks 2D, and you check that, and that's it. You can do that. You need to do that only once. Okay, so this is your fully three-dimensional problem. So let's start with the 2D. Okay, so as I said earlier, you can do simplification, 2D simplification, and when you do 2D simplification, okay, you take a cross section. Okay, so let's go straight to the cross section. So you have an option between 3D, 2D only, or both. Okay, let's just show you just the 2D. Okay. All right, so this is our 2D. We did the 2D simplification, took a cut, okay, and this is your 2D analysis cut. Okay, so now in the 2D, we did several studies. I'm going to show you all of them. First one is we did the force versus air gap. Okay, and of course the how to apply material. It's really very easy. We have a plenty of webinars and presentation on our YouTube channel. We encourage you to visit them. And if you still have some questions, of course, you contact us. So how to apply coils, boundary conditions, material excitation, all of that straightforward. But I'm just going to show you the parameterization, okay? So the parameterization, in this case, we have different parameterization, the housing and the air gap. So first one is the air gap, the effect of the air gap, as we showed you some of the results earlier. Okay, so as we parameterize the air gap, okay, so these are the results. First set of the results at each scenario, okay, we're going to have the force. Okay, so you can export it, print it, or if you wish, you can plot it. So I'm just going to plot. I can show smooth, and I can show the markers, circles. Okay. All right. So this is my first conclusion, as we said earlier. So this, based on the parametric study, not all air gaps will work. Some air gaps will work, some won't work. So this is one first conclusion that you can draw from this parametric study. So we want to have something 400, 500 Newton more. It depends on how heavy is the machine. But even for a small car, you're going to need around 500 Newtons. So you can't have any air gap. So this is one set of results. Of course, this if you want to see them in a text format, okay, you can of course save, export, and so on and so forth. Okay. All other quantities are, if you want to look at the other quantity as a function of the scenario or the air gap size, you can plot it. All right, so these are what we call tabulated results, table results. Another set of results is actually the field results, B. So you can have fringe plot, vector plot, contour plot, feed line plot. Let's just quickly show you a fringe plot. So this is my fringe plot, okay, at different air gaps, okay, and I can also superimpose it with the contour lines, okay? And I actually should be able to animate this versus scenario. Okay, as you can see, yeah, these are different scenarios, and of course, your flux density varies a lot. Okay. Of course, as we said earlier, the smaller is the air gap, the larger is the force. All right, so this is one set of results. You definitely can do, if you wish, a vector plot, or straight you can do field line plot straight. Okay, there you go. Okay. Same thing, you can do that for the magnetic field. You can look at the current density, and then what these are field data, be your age, current, magnetic vector potential, so on and so forth. You can also, in the what we showed you earlier, in the plotting, if you don't want to do it from the results table, you still have a chance to do it from the electromagnetic parameters 2D. So this is your force, you could say add, and this is the same plot I showed you in a minute. This is the parametric study of the area gap. Okay. Another study, as we showed in the PowerPoint presentation, is the is your plot for the different housing thickness. Okay, and if you may, I can animate also versus scenario. Now you're going to see the housing is becoming larger and larger and larger, and again smaller and smaller and smaller. And okay, so I can see how my magnetic flux density changes, and of course I can also look at my plot. I plot a scattered or two linear. I can do the F, okay, force, and again I can change the circles. Or okay, this is what I showed you earlier in the PowerPoint presentation, the same plot. So at a certain thickness of the housing, the force becomes very small and it's no good. Okay, so there is a trade-off. Of course, we know, as I said earlier, thicker housing means more expensive. You have to more steel, heavier, so on and so forth. But you know, in order to produce enough force, you must, respect the physics of the problem. Physics tells you that, hey, if you want to have this force, you have to have this much air gap, you have to have this much thickness of the housing. Okay, another study we did is the parameterization of the current. Okay, so I did 3, 6, 9, 12, 15, okay, current in the electromagnet or coil. And again, I wanted to study the effect of the current. And again, I can plot my force. And there you go. I can smooth it, put my markers on, okay? And again, this one, it tells me at what current, okay, I'm going to start having the plunger start moving, okay? So again, as you can see, 6 amps or a little more, that's how much current you're going to need. So this is also important. So bottom line is this. So with the EMOX2D, with the parameterization, you can do a lot. You can do a lot. You can see the field, current, and you can look at your force. And again, for actuation, for in this case, the actuation is the most important, okay? All right. we can do also a transient analysis, okay, or dynamic analysis, okay. So force at static position. So this one is without motion, okay. Um, I can again look at, but this is transient. So if I look at my electromagnet or coil, it's applying a DC voltage, okay, and this I can also do versus time, okay. So this is a transient analysis, unlike the previous study is static analysis. Okay, I can do with motion coupling. So this is with motion coupling. So only thing I need to do when I do properties in my study, I do coupling analysis. I say translation motion and specify my motion. It's dynamic velocity, dynamic analysis. Okay, and same results. I can do my 2D plot. I can versus time linear. Okay, and I can do my force. And now, okay, as a function of time, you can see my force. And here I not just the purpose here is not to actually move the actuator. You don't have any force, but just to show you this particular feature that we have in EMS is the actual coupling to motion. So you can see your force as a function of time. Okay. You can, of course, you can plot. Okay. And t equals 0, then I can animate versus time. Okay. Okay, it's slightly moving, okay, as you can see. Okay. But this is not a parametric study. This one is an actual motion study. The motion study is dynamic because it takes into effect the eddy current, because as you know, eddy current comes from two sources. If the current or voltage is changing as a function of time, or if there is motion. You can have just magnets without anything changing uh, with respect to time. Yet when there is motion, okay, Faraday's law tells us that there is an eddy current. So this is the motion analysis in 2D. Okay. Uh, Same thing here for 43 volt. Okay. And then I can if I want to see the effect of the voltage, I can come over here and say, compare results. Okay, I want to compare now my F, my force, okay, as a function of time for this 3 voltage. That's what I showed you earlier, right? So, um, so the blue is 23 volt, red is 33 volt, and the green is 43 volt. Okay, and now with the motion dynamic analysis, okay, I can see definitely I have a higher force with the higher voltage, but again with higher voltage, I'm going to have higher losses, and with higher losses, I'm going to have higher temperature. So this is a design trade-off that you have to take into consideration. Okay, um, so I can generate a report at the end, so I don't need to take notes. So I can just customize my report and do an HTML, and this is going to dump all the pre and post processing data. Okay. Looking at my watch, it's already 40 minutes. So let me, so this is a 2D. Let's just now go to, one feature. I cannot not show you the plot results. Okay. One feature that I cannot not show you is when I do 2D and 3D. And this is really cool. Okay, so your 3D model. Okay, I'm taking a section and I'm actually showing you the 2D solution out on 3D model. Okay, all right. With that, I'm going to go to 3D only. Okay, and I'm going to go to EMS and now to 3D only. Okay, so 3D only is the same idea. Uh, Look and feel is the same, except this is actually fully 3D. So fully 3D, I can again have my results, uh, the torque, current, inductance, flux linkage. Of course, this is transient losses. Uh, so mechanical, electrical parameters, all on my table. And again, I can do the plotting. This is my field plot, okay? And I can animate, as you can see, the plunger are going to start moving. Okay, there you go. Okay, it's a small movement, but the one thing that I wanted to show you, which is very important, is the coupling. The 3D actually uses SolidWorks motion. And you know SolidWorks motion is a very powerful motion because you can do 6 degrees of freedom with all exotic motion settings. So only thing you need to do, okay, is simply say couple to motion and choose which SolidWorks motion you would like to use, okay? That's all. Just couple to motion and you do that. And then as I showed you earlier, if you go to the motion, okay, if you want to animate, you can play. There you go. Okay. So this is your SolidWorks motion. Okay. So let me go back to the plot result. So again, the table results, you can plot linear, okay, and my actually FZ, okay, add, okay, and that's my force as a function of time. Okay. Whatever I showed you in 2D is available in 3D for the field plot, the table. It's the same idea. Okay. Uh, this study is actually coupled to thermal, and in the properties you go and say coupling analysis and you say thermal coupling, and this transient you can have both steady state and transient thermal. Uh, Same idea, field plot, but one thing that you have here is the as you can see, this what we call integrated thermal solver. Why it's integrated? Because you don't need to run electromagnetic, export to another file, another program, another window. No, none of that. Okay, no mess here. It's everything is what you see, what you get. Okay, so the electromagnetic input and the thermal input. Thermal input, it can be any of these regular thermal stuff, or in this case, just have convection, so air cooling, okay? And you get the results as the input is split to two, okay? So you make no mistakes. So the results are also split to two. The results are the electromagnetic results as well as thermal results. So I can look at my temperature distribution, okay, in the housing. And I can animate it also as a function of time. And when you say it's function of time, is in this case, there's no coupling to structure, but the voltage changes a function of time. So, of course, you have the gradient, the temperature gradient, all that stuff, all of that goodies, heat flux, you know, so on and so forth. So that's coupling to thermal. I also have another coupling to thermal with temperature-dependent material. Okay, again, you have the electromagnetic input, uh, thermal input, the post-processing. Okay, and there's another feature. Okay, this one is a temperature. If I want to look at my temperature, okay, suppose I want to see the temperature between, say, this point and this point and this point, I can simply say, okay, and I have to choose a time step. There you go. I can plot the temperature, okay, on that line segment. I can do that actually even for, I didn't show you this for the flux density. You can do that as well, okay? So if I want to look at 3 points here, I can plot on those segments, okay, the flux density, how it varies as a function of the distance between segments. So to conclude, okay, already 46 minutes passed, so I don't want to take more of your time. But to conclude, the EMS and EMWorks 2D together allow you to really study all aspects of your solenoid actuator. Okay, and this particular case is for one particular application for the automatic manual transmission. Okay, it can really be instrumental in your design, early on in your design, so you know how to choose a material, how to size your actuator, and how to design around thermal, because we can do thermal analysis. We also have coupling to structure. We didn't show it here, but in other videos, we have also coupling to structure. Okay, with that, I would like to finish this presentation. Sorry, it took too much time. And again, it's time. And again, of course, I would like all to thank you for bearing with us. Now, I'm going to move to straight to the question and answer. Okay, thank you again. All right. So the question is, oh, who is the manufacturer? Okay. Well, the manufacturer of this one, I actually don't have it, but I know who asked the question. I'm going to send you the name of the manufacturer. Okay. Will this simulation work with CATIA 3D? No, it works only with SolidWorks. Yeah, I think Steve said Isuzu, one of the slides is probably Isuzu. Okay, but I have to double check to tell you the truth. Somebody asked about SolidWorks motion. Can we do springs? Yes, of course. In the 3D, the 2D, you cannot. In the 2D, you have simple motion, okay? But in 3D, because we use SolidWorks motion, okay, and you know SolidWorks motion is very advanced. It's based on atoms, right? From the 60s, this motion program, okay? And you can do springs, you can do friction, you can do all kinds of, you can do actually 6 degrees of freedom. Of course, it's not needed for this particular application. You wanna move only in one direction for actuation, right? In one direction is already complicated enough, but you can. How do the coil configuration for the flow of the current? Yeah, so because in parameterization, okay, you can the flow of the current, I think the direction. How do you coil configuration for the flow? Yeah, so yeah, the direction, you know, because in the 2D is straightforward, right? It's in or out. In 3D, you have to choose the face normal to the current. But it's just one click, you can switch the current, you know, in direction back and forth. It's very simple. Okay, my application engineers help me right now, and it's manufactured by LEDEX R Company. LEDEX R Company is the manufacturer of this actuator. Thank you. Yeah, in this design, there are no permanent magnets. But if you want to see something with permanent magnet, it's just either contact us, we can do a customized web demo for you, or just visit our YouTube channels. And we have hundreds, literally hundreds of videos with all combination of permanent magnet only, permanent magnet with coils, coils only, so on and so forth. Yeah. So, all right. So it's never late to ask a question. So if you don't have a question right now, you could have a question later on. If you do, please contact us. Write to us, support@emworks.com. Call us, email us, chat with us. We'll be glad to answer all of your questions. And again, thank you. And just a heads up, next week you're gonna actually every Thursday we have a webinar. Sometimes a high frequency for a high frequency simulation, HF works mostly for antennas and microwaves and 5G antennas and so on and so forth. And another week is mostly for motor generated electromechanical stuff using EMS and EMOX 2D. And of course, if you would like to uh, uh, yeah, Steve asked if there are transformers coming up. Yeah, yes, of course. We're gonna have a webinar on transformers soon. Just stay tuned and check on our website. We have the schedule, okay, for the webinars. But we already have transform webinars. I think the marketing support, they're gonna probably send you some of the webinars that we did on transformers. We did several transformer uh, webinars, and of course, if you want to have a one-to-one web demo, we can schedule one for you. Just ask. Okay. Okay. Thank you again, and have a nice day.